السلام عليكم ورحمة الله. الآن إن شاء الله ننتقل لموضوع ال vector spaces. The vector spaces is the place, the container, the holder that holds vectors, and we said vectors are objects that can be added together or multiplied by scalar quantity. So if we have a vector that we can perform those two main operations on them or on it. Okay, so this is called a vector space. So we need to formalize, we need to build concepts in order to reach the vector space. So the first thing that we do is we define a group. A group, first of all, a group is a special set. Is a set with a few properties. Set with properties. Okay, so what are those properties? The first of all, we need to define some operation on that group. So let's denote this operation by this symbol. Okay, this is not a multiplication, this is a symbol for any operation that we have. And this operation takes two inputs from the same set, G. This is called a calligraphic G, and gives a single output in the same set. Okay, so a group is the set and the corresponding operation on it. So if we want to call this pair a group, several conditions must hold or be satisfied. The first one is the operation must be closed under G, meaning that this condition must be satisfied. Mathematically, say that for all, so let's write it here. This statement means the following: for all x and y belonging to calligraphic G. Okay, so the operation, the output x operation y belongs to G as well. Okay, the second condition is associativity. So the ordering of the operation does not matter. So this means the same thing for all x, y, and z belonging to the set G. X operation y, then operation z equals y operation z, then operation x. Okay, now the third condition, there must be a neutral element. What is a neutral element? This means there exists. So this, let's write it in a nice way. It's not that nice. This means that there exists at least one element. There exists an element E that belongs to the set G, such that for all x's in G, the x operation E equals x, so nothing happens to x, and E operation x, so if we swap the order, we still get the same output, which is the same element. So let's say, for example, here, okay, let's open a page and see. Okay, so let's define the neutral element here. Let's take an example for neutral element. So a neutral element example. So let's say that we have a set R. What is R? The real numbers, say, and we want to find the neutral element for the normal addition operation. So how we do that? So okay, say we need to find an element E that belongs to R such that can put colons here, such that for all x belonging to R, x operation addition mean E equals E addition x equals 0. So what would be this neutral element? Sorry, not 0, it would be x itself. The neutral element is 0 in this case, right? So let's take another example. Here we have the same set, the real numbers, and the multiplication. So let's put like a dot here, right? A dot. Again, the same thing. There exists an element E that belongs to R such that for all x belonging to R, we have E dot x equals x dot E equals x. So what would be this element? For the multiplication operation to be unity 1. Okay? Okay, let's take more examples for neutral elements. Let's take them for matrices. Okay, so here now what we have is R2 cross 2, and the operation is addition of matrices, so it's element by element addition. Now we're looking for a neutral element E that belongs to R2 by 2 such that for all, let's say x capital here, x small, no problem, x small belonging to R2 by 2, we have E plus x equals x plus E equals x. So what would be this neutral element? What do you think? It's the all zero matrix, right? Okay, another example for the same set, R2 by 2, and now we want the dot, which is the matrix multiplication. So matrix multiplication again, let's go by definition. There exists an element E in R2 by 2 such that for all x's in the same set, we have E dot x equals x dot E equals the same x. So what would be this element here? It's the identity matrix, right? It is I2, right? Okay, so this is the neutral element. Okay, so what's the second condition, or the fourth, the fourth condition, which is having the inverse element. So what is the inverse element? So you say that for all x's in the set G, there exists a y in the same set G, such that when you take the operation x, operation y equals the neutral element, and y operation x, this is x capital, equals the same element, which is the neutral element. Okay, so let's go back and see the examples that we had here. So let's add another page. Again, now we have the set of real numbers and we have the addition. What is the inverse element here? So we said, okay, there exists. Okay, let's be precise. So what was the condition? What was the definition? I think there exists, right? Or for all x's. For all x's there exists. So I mean, if we flip them, there's not. It's not a big deal. Yeah. So we say there exists an element, or for all x's there exists an element. The same thing. So there exists an element in R such that for all x's in R, so this I think element is y, right? Call it y. Such that y plus x equals x plus y equals the neutral element. Okay, what is the neutral element for the addition? We said it's 0. So in this case y equals minus x, and minus x of course belongs to R. That's good, right? Okay, so the second example that we took R, and the operation is the product. So again, there exists a y in R such that for all x's in R we have y dot x equals x dot y equals the neutral element. What is the neutral element for the dot or the product? It's 1, right? So here we can say that y equals 1 over x, but we have a small caveat here. When x equals 0, let's put it in a clear way, then y goes to infinity, and this does not belong to R, right? So we have an inverse element for all x's except 0, right? That's good. Okay, so let's look at the other two examples regarding matrices or square matrices, right? Again, so we have R 2 by 2, and you have the addition, matrix addition. So the neutral element y, or the inverse element y, in R2 such that for all x's in R2 by 2 you have x plus y equals y plus x equals e. What is e? E, if you remember, it's the all 0 matrix here. So this means that y again is minus x, right? And it belongs to R2 by 2. So this is a simple one. What about the matrix multiplication? This should be like a dot. Okay, there exists y in R2 by 2 such that for all x's in R2 by 2 we have x dot y equals y dot x equals the neutral element. Okay, so what is the neutral element here? It's the identity matrix. Okay, so this means what? This means that y equals x inverse. Okay, so does this x inverse belong to R2 by 2? Now be aware that not all square matrices have an inverse. Not all square matrices have an inverse. For example, you cannot find if x equals 1 1 1 1, this does not have an inverse. Why? Because it's rank deficient, meaning that the same column is repeated, so the rank of x equals 1, right? Just to write it in a neat way. Rank of x equals 1, which, it's less than the dimension of x, which is 2, meaning that it's rank deficient, meaning that you cannot find an inverse for it, right? Okay, so now I think we covered the conditions here, 4 conditions. Now let's look at examples here. So the first one says that the natural numbers and addition on natural numbers is not a group. Why? Okay, now we need to check the 4 conditions: the closure, associativity, a neutral element, and the inverse element. The existence of a neutral element and existence of an inverse element. Okay, now we can readily say that the addition of natural numbers will give a natural number. So it's easy to say that, easy to show that. Actually, it is intuitively shown, but not analytically proven in a simple way. Okay, so we have the so let's write it down, right? Let's write it down. Okay, the set of natural numbers and addition, right? So let's say x and y belong to natural numbers. So we can say that z, which is x plus y, also belongs to the natural numbers. So it is this set, it is closed, right? Under addition, they say, under addition, no problem. Okay, the second thing is that associativity, so x plus y equals y plus x, right? It's very simple. Now the neutral element, so let's put here like this, neutral element. So we say that there exists a neutral element in N such that for all x in N there exists, or we have, x plus e equals e plus x equals x equals x. Now this element is 0, and 0 does not belong to the natural element, natural numbers. So hence the natural element defined with, or with an addition defined in it, is not a group. Okay, so what is the next example here? It is, okay, if we add the 0 elements, it's still a group. Let's go down and check go down, check, so we add another page, say okay. So we have n and the addition, right? So now there is, as we say, now we solve the problem of the neutral element. There is a neutral element, which is what? Equals 0. Again, how about the inverse element? So there exists y in n node such that for all x in this n node, the same node, y plus x equals x plus y equals 0. This means that y is minus x, and this does not belong to the natural element, because the natural elements, they do not include the negative numbers. Okay, so this is the trick in this thing, this case. Okay, now z here, it's the, so z, what is it? Okay, z, let's write it here. Z is if you like, can squeeze it here. It's n positive with n negative with the 0. Okay, so here is this is not a group. Again, this is not a group under the product, but it is an abelian group under the addition. How? So if we include the negative numbers, I think we solve the problem, right? Then z is a group, but we add that, let's say that x, so here that we x and y, they belong to z, then x plus y equals y plus x. So this is which condition is it? It is commutative, right? So this means it is a group, and it is abelian group for the addition. For the product, it's not a group, because we don't have an inverse element, because the inverse element is 1 over x, and 1 over x does not belong to z. Actually, it does not belong even to r, as we seen earlier, because 1 over 0 is infinity, and infinity does not belong to the real numbers. Okay, z to the power n is an abelian group, right? Let's see that. Okay, let's see that. Z to the power n. Go down, 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 down. Okay. Let's add another one page, right? And start from the beginning. So you have z to the power n and have addition, right? So okay, first thing, closure. So let's say we have x and y. They are vectors belonging to this. Sorry, let's write it in a neat way. Okay, so this is z to the power n. Now x plus y equals c, or z, small z, and this belongs to, of course, the the same set, so it's closed, right? It's easy to show that. Okay, the next thing, associativity, right? So if we have x, y, and z that belong to this set, then x plus y plus z equals x plus y plus z, and they belong to the same set. So we have check this thing. Yeah, now we want the neutral element. So there exists a neutral element in this set such that for all x in this set, again we have e plus x equals x plus e equals x. So what would be e? E is the all zero vector. So we had n vectors, right? And this belongs to the set n. So we have a neutral element. So what about the inverse element? Inverse element, there exists y in this set such that for all x in the same set we have y plus x equals x plus y equals e, which is a neutral element. So what is y? Y is minus x, and this belongs to the same set, meaning that it's a group, and it's an abelian group since y plus x equals x plus y. So we can easily see that it's a group, and it's also an abelian group. This is good news, right? Okay. Now we've shown this is a abelian group. This is not a group because 0 does not have an inverse element. This is a abelian group. This is the same case as z to the power n. This is a abelian group, right? And this is not abelian. It is a group if the elements are regular, meaning that the matrices, they have full rank. Okay. Otherwise, as we've shown, that it's not a group, right? It's not abelian. Why? Because a multiplied by b does not equal b multiplied by a, right? It's not always the case.